Good afternoon, everyone. I hope you are all having a lovely day. And yes. So today we are going to be talking about building custom neural networks in the Wolfram language. So we should have some polls coming up throughout the course of the webinar. So please do answer them because they're really helpful for us for future webinar content. What works out, what's not so good, and just getting like a understanding of our kind of clientele who's coming here. So anyway, let's get right into it. So I'm going to give a bit of an outline of what we're going to talk about today in this webinar. And so, we're going to kind of like, build it from scratch, kind of like go over some of the basics of how AI can be used, exploring what neural networks really are. Then, how can you can build them in the Wolfram language? And, a key focus here is like, the question of whether you need to build a neural network. Like there's a lot of stuff that's already like pre-baked into Wolfram language to do with neural networks and classification prediction tasks, which kind of alludes to the point, do I actually need to? Um, so yeah, we'll look over some of that. Some of the pre-trained models, we'll look over those a bit. Um, and then yeah, we'll kind of summarize that all off. So anyway, let's get into some just like, get some refreshers, some quick examples, like what can we actually use like AI, artificial intelligence for? And a really good thing, um, key skill of AI is to do with like, these data science prediction kind of classification style tasks. So here we've got like, in Wolfram language, you've got so many like ultra high level functions like facial features where we can just kind of like input into it, for images and then kind of like extrapolate from those raw images in, get some kind of cool insights into, the actual image themselves. So here we've got a photo of a man, and it's telling us, it's giving us insights about the man. I don't know if he's quite 55 or 43. I don't know how accurate that is, but it's picked up reasonably well that he's male. He's angry in this photo. He's happy in this photo, and you know, Wolfram language has a bunch of these high level functions which kind of like streamline the whole process of this rather complicated task. You've got there's a lot of machinery behind the scenes going on with something like facial features built on top of a lot of neural networks, and it's just pretty cool to see that. Also got a bunch of different, text summary things. So, if I want to get a summary of a piece of text, what's a good summary of a piece of text? Uh, I'm happy to today I went to the shop. Bit of an ad-libbing exercise, but wonder what it's gonna come up with, or maybe this one isn't set up quite right. Oh, no, okay. So yeah, you've also got access to, there's a bunch of different baked in things. It's picking up, I think this is, one of our higher level, like, sentiment analysis style things. So it's picking up that it's English, and it's wrapping this in a Wolfram language entity, which is like, a very, again, high level representation of the raw thing. So this is representation of the English language here. Um, I think it's giving this bit of a dated piece of code, but it's, got Facebook topics, it's giving an overall sentiment, whether it's profanity, contains profanity, a bunch of cool different summaries of text, all baked in into the Wolfram language, just like right at your disposal, which is pretty cool. Image location, I'm probably going to let you play around with this just as we play, but basically, again, you can give it images and then it can like obtain vast amounts of information at your own disposal. Other things we can do, so those are more like, classifying raw data into, distinct categories, but prediction is this other, like, rather, essential seminal, data science task where you're trying to expand out from your data set and predict for an unseen value. So, one such task, if we, like, stick to the realm of images is, given a in this case, we've got a black and white photo of a dog. Can we predict what might, what the black and white photo might look like in color. So we can use, one of these, resource functions, which is, it does a pretty reasonable job at coloring in this black and white photo. Um, those of you who don't know, resource functions are, these kind of like online curated, functions which are written by, either Wolfram, users or, people working at Wolfram Research, or more general. And, they kind of like, let it expands out the, Wolfram language into a, like, higher dimensional space by covering, things that aren't necessarily covered by the, 8,000 odd functions we have baked into the raw language. Um, but yeah, this is just a nice, cool example of things we can do with AI, that we are predicting, the colors for this photo. So more kind of prediction-y style things, so we can import in, neural networks, um, from one of our repositories. So, as Wolfram users, you have access to a bunch of different repositories. There's data repositories, actually data repository and neural networks repositories are the 2 that come to mind at the moment. But, again, similar to like resource function, we've kind of curated a lot of different, stuff for a particular realm of computation. So here, neural networks, and because of this, you can just like import them into, your, notebook. So I can just call net model on this particular named transformer. So, GPT transformer trained on book corpus data. I think this is going to be like some sort of, neural network which is gonna be able to predict next, words and sentences. So here we've like imported that, assigned it to a symbol, and then we're going to apply, a sentence to that symbol, and then, we're effectively feeding that into the neural network so we can get a prediction output. So she got out of the car is what this particular neural network is thinking is most likely as the, next argument to this. It's kind of just a cool prediction, and it sounds pretty, realistic. Um, Also, there's a bunch of different, LLM-based functions, one of which is LLM synthesize. So this is, just directly prompting an LLM. So I can, what's it gonna do? It's really just gonna send off an API request to, I think, AP OpenAPI, so we're probably gonna be using one such model. I mean, it's given us a whole different bunch of different things, but, you can really feed it anything like, hello. I can say hello to my LLM, and, it's just nice to have that union of, we're bringing the power of LLMs into our notebook, environment. We also have, notebook assistant, so, this is this cool Wolfram technology where we, just get an example. So, plot a how do I plot a molecule? And hopefully it goes off, and so this is, actually use calling an LLM, but we've also kind of like given it a bunch of auxiliary training data in the form of semantic search indexes. So it's like not just an LLM that has the knowledge of the base LLM, it also has, we've kind of given it auxiliary training data in the form of, Wolfram language functions. So, if you have a particular task that you can explain in like pseudocode, then you can, tell that to the notebook system, and then it can go off and help you, explore how you would solve this problem in, the Wolfram language, which is pretty neat. Um, so yeah, very, very powerful technology. Semantic search as well is also a very cool thing. So you can do semantic search, on a, base, search index, which you have to create yourself. I don't have access to it right now, but this is a really cool new part of the language, where you can, in what we've done, we've kind of like retrained our LLM, or not our LLM, OpenAI's LLM, to be particularly good at Wolfram language functionality. It can find Wolfram language functions in vector space, which is far more efficient than, or at least it gives you, AI's access. It gives AI access to Wolfram language functions to an extent. Also, what else we do? So, we can pull in, we can perform feature extraction. Um, we can put in another particular model, another particular LLM. We can extract features from that. Feature extraction is this pretty kind of almost an art in of itself to, boil down raw human understandable data like a string word such as king, and then encapsulate that in vector space. Because obviously, for those of you who don't know, neural networks or AI or computers don't understand English in the slightest. They only understand vectors, raw numbers, and this has to be eventually kind of compiled or transpiled further and further down to, raw binary. So, there's a lot of machinery going on. Probably won't need to talk about compilers right now. A very interesting topic nonetheless. So these are more just like general examples of what you can do with AI. How you've got network repositories that you can just pull raw pre-trained neural networks into your environment. You can use them for a bunch of different things. You've also got like image restyling kind of um, stuff, all very interesting. Again, more kind of like data science-y, raw tasks that are suited to LLMs, kind of like anomaly detection. So yeah, let's run through this. So here we're just taking a random sample of some of our resource data. So here we're just pulling in the MNIST training set, which is I think it's like huge assortment of labeled handwritten images to their ground truth. So a 7 is mapped to a 7, and, I think I can even look at that, look at a short version of that. So, yeah, bunch of different, uh, hand-labeled images. I think that's just training. And then, yeah, so, in the realm of anomaly detection, we can use something like, anomaly detection. So we've used this function to create a detect function. So then we can go and, apply use find anomalies to kind of like go about using a detector function to go and like find more anomalies in data. And as you can see, it's done pretty well. It's picked up that one of these images is not quite right. This picture of a monkey isn't necessarily um, you know as related to the other images. It's not a number. It's a monkey. Um, but anyway, so that's like raw, like a big like, high level overview of um, sorry, everyone. I think we were experiencing some sound issues, but hopefully this is a little better. I'm going to go ahead, um, assuming that it is. But okay, so where were we? We were in. So we were just kind of like we didn't quite capture what we were talking about. Most of it is just kind of summarized in these examples. They're somewhat self-explanatory. If you don't understand them, then I would recommend checking them out, like the individual function documentation. It's a very good resource for learning about Wolfram language in general. But again, apologies for that. Okay, so let's actually get on to neural networks. So, what we were talking about earlier was more like to do with overall uses of AI, but like neural networks are kind of like serve the back end technology behind how they actually come to these classification or prediction outputs. And you can kind of think of neural networks as like these. It's like this mathematical model that's kind of like inspired by the brain that can learn kind of patterns from data, and it'll adjust individual connections or nodes to kind of output a correct um, output from a given input even. So you've kind of got this, three-layered approach to it. So you've got an initial input layer, you've got a hidden layer where like, a bunch of different transformations but can occur to input data. Um, and then, you've got this like almost like a signal going from the input to the output, which is going to be eventually output a kind of like classification or prediction style thing. So it's you can think of it like interconnected decision units that are kind of passing signals from inside itself to outside the network. Um, so the whole point of training a neural network is to kind of like reassemble these individual um, nodes and individual weights and biases to kind of incorrectly map from uh, inputs to outputs. In the training process, you're feeding into the network, you know, raw data which is mapped to ground truths. So earlier on, we were looking at some photos of handwritten images. These would be mapped to the ground truth of the actual digit that it represents. So then, this mathematical model can go ahead and kind of like learn the complex patterns underlying the data to be able to go from a correct input to a correct output, or an input to a correct output, I should say. Um, and you know, there's a bunch of different ways. So you've got this input layer, this hidden layer, which kind of like is serving this like black box. So okay, if we have missed a bit, so we were kind of like describing neural networks as this brain has individual synapses, which can be these are serving as the weights and biases, which can kind of be strengthened or you know uh, not strengthened in such a sense, though, that you're kind of building these decision pathways from raw inputs to outputs. So these kind of networks have there's a bunch of different categories for them, and these categories are kind of like quite related to the function of the raw network themselves. So in the sense of a feed forward neural network, it's probably the most simple one. It's just passing data forward from input layer to the hidden layer to the output layer. Convolutional neural networks are kind of more to do with like aggregating data and its surrounding points, and this is particularly good for like image processing to kind of get information about not just the locate like individual data, but surrounding pieces of data. Again, long-term memory, sequence-to-sequence transformer. These are all unique neural networks in their own sense. Um, but yes. Okay, so how do you actually go about using neural networks for actual data science tasks? It's obviously a cool technology. I'm sure everyone's played around with ChatGPT, but like actually using it for actual data science purposes is pretty key to harnessing the power of neural networks. So there's kind of like this general pipeline which you should be using to get the most out of your neural network and actually, like developing itself. So first of all, okay, so yeah, so what I was like kind of saying, just to recapture what we were talking about, kind of going into neural networks, they're a back-end technology behind AI. Not all forms of AI, but it's a particularly powerful one that is grown in scale and usage because of GPUs being widely more powerful. Okay, so how do you actually go about building and using your own neural network? So there's this development pipeline which should kind of underpin your thought process when trying to solve stuff. Okay, gonna keep a bit more of an eye on sound issues. Hopefully this has all been fixed. So okay, but what do you want to do first? So we're working in the realm of data science kind of tasks, and you are obviously going to want to first of all acquire some data. This is going to be this is more towards the development of creating a trained neural network. There's more to it behind the scenes of like actually assembling the network themselves, and we'll look at that a bit later on in the webinar. But if you've got like a pre-built webinar, then it's going to be in an untrained state. So you are going to need to get your data and then you are going to want to train your model so that it can perform well for a particular given. It can learn patterns from the data, and then it can go about the process of extrapolating onto unseen data, and you can get these nice prediction style tasks performed or classification style tasks. So you get your raw data, and then you're going to want to separate it into two distinct units, into the training data and your testing data. So usually you're going to be wanting to split this into about 75% training data and 25% testing data. Then you're going to want to be going to encode using encoders to encode that raw data into vectors. So we said this earlier, hopefully might have not got across because of the sound issues, but LLMs only understand they can only perform math operations. So it can only work with vectors. It can't work with the raw data. So you've got to extrapolate the raw essence of the data into vectors, and this is this art form of feature extraction, which is quite an important part of the process, and getting a more accurate representation of your data in terms of vector space, you're going to get better results in general. So once we have separated our training data and testing data, encoded it into vectors, then this is when we can perform the training process, where the model itself will in the training process kind of reassemble itself, and not in a physical sense. It won't change the kind of structure of the predefined network, but it will be able to alter the weights and biases involved, so that it's able to consistently map the input data to the labeled ground truth. This is what's going on in the training process. So once you then have a trained model, then you can go towards the testing stage, and this is where you use the other facet of data to kind of validate, is my model actually doing what it's supposed to? Do I need to rethink my training process? Do I need to rethink my training data? And we'll look at a bit of that later on. Then once that's all done, then you can go ahead and actually use your neural network, and then it's going to be outputting vectors, which are going to be you're going to have to return that into a human readable format. We don't understand vectors, but the LLMs, the neural networks do, and then you're going to get the results, and you can see how well it's done. So training process, you're going to want to get data, represent it in vectors, set up the model, train it, test it, and then validate it. Kind of like a key point I want to make is in in the AI machine learning field, you don't really want to be focusing on why it's working. That is the kind of neural networks are kind of learning in dimensions and vectors in a kind of like space that we just quite simply can't understand. It's learning patterns that we can't see. So that's why we kind of refer to it as the black box, because we won't be able to get an understanding of what's going on. It's just getting building a kind of function to go from input to output, but in a very, very complicated way in many cases. Also, you can get like nice measurements, and we'll look at that in a bit. So before I actually go into I'm going to carry on. I'm sorry if you're hearing sound issues. Okay, so one thing I do want to mention is whether you actually want to build a neural network, and this is going to be kind of like a drive home point of this webinar. Like, in the Wolfram language, you have an awful lot of ultra high level functions which can kind of automate this process all for you. We've been doing this. We've been in the AI space for a long time, and the computational space for an even longer time. And sometimes it's okay to kind of like let us do the work for you and use some of these like very complicated and curated functions like classify, which you can really just feed it data and then build a model which is most appropriate for your particular data set. And to be honest, in most circumstances, this does perform pretty well. So unless you're doing pretty highly specialized stuff, it's almost worth just checking out some of these functions which we already have, so that you can kind of like get into it. It's also just a nice way to kind of like get into ML to AI. You can use these functions as a like base kind of way to get your mind around what's going on, and then you can go on beyond and start to build some of your own stuff. So anyway, let's look at a quick example. So using the Titanic dataset, again, we've got a bunch of different, this is some of our resources baked into the language. And we can go ahead and build a classifier with this classify function. This goes off, looks at the data, kind of it automates the entire process of building a classifier for you. So in this case, we're using just nearest neighbors, which is a ML method, to go ahead and so I think we are working out, given input data, what is the probability that this person will survive? And we can also extract that out from the Titanic classifier. We can get the probability of this input data, whether they died or survived. So first class passenger, age 50, male, is 55% likely to die, 44% likely to survive. And so they are, when you're working with classifiers, you're never going to get a like kind of discrete answer. It's more going to be a range of probabilities. ML and neural networks, they are kind of working with statistics. Then it's less computation based. There's computation involved in describing those statistics, but it's more working in the field of probability. So for this reason, you can never like categorically get an AI system built with ML methods or neural networks to categorically say something is true or not. So again, we can kind of like play around with our data. So we can just replace the data set. We'll kind of like reform it to not predict the survived or died outcome, but we can reform it into this different pattern using this replace all. And then we can go ahead and do some prediction work. So we're using this other ultra high level function called predict to go ahead and, given some input data, will they so we're generating how old we think they are. So with one of the beauties of the Wolfram language, we've got automation kind of baked into everything, and we can deploy this to the cloud, and then we can go ahead and we've got this nice little infographic which I could send to a friend, a colleague, whatever. I'm sure your uses will be more more unique to your problem, rather than working out the Titanic survival probabilities. This is more just to show off an example, and so I can go ahead and get this nice infographic of whether they died, survived, all automated for you and in the cloud for easy deployment. Okay, so that's all well and good. So you've got these like really nice automated development pipelines which do an awful lot of the heavy lifting for you. But if you are thinking of like going down the manual path, then you do get a lot of benefits. Yes, it's complicated, but it's an awful lot more customizable. You get a lot more choices in terms of model types, data types, how you want to fine tune the model. You can like alter the dimensionality of the outputs, so these can be richer, more complicated. What makes a machine-made Picasso-style painting good? You get the ability to really describe what you want for your given circumstances. A lot more degrees of freedom, but this is double-edged sword. You do need to have specialized knowledge. You do need to have a reasonably good grasp of programming, and this is going to be a hard thing for a non-programmer to do. But Wolfram language does make it slightly easy for you. Okay, so let's talk a little bit about the design of how you'd go about building your own custom network. So I'm going to point you towards these tech guides, which are pretty helpful. So we've got a bunch of different functions involved with neural networks online, and also have general tech notes on how you can actually go about building your own neural networks. So would recommend checking these out for future reading. But we're also going to go through a little bit today. So again, we are going to be, making a neural network with input layers, hidden layers, output layers. That's still relatively the same, but there's a general architecture patterns that you want to stick to. So you quite often want to be alternating linear layers with non-linear layers, and often the type of layers you want to use will be representative of your data. If you're working with pretty simple linear data, oftentimes you don't want to be overcomplicating things. You probably only want like one linear layer involved in your neural network to be able to map to your linear layer. So there's a bunch of different functions involved with these linear actual layers themselves. And these are going to be very the choice of which layer you want to use is going to be dependent on your use case. So, I think convolutional layers are like nice examples of things that you want to be using for kind of image recognition. Anything to do with images, convolutional layers are pretty good. And then, there's many different layers, which I'd recommend checking out. There's about 60 in the Wolfram language. So these individual layers are actually just like trainable models in of themselves. And we're going to look at a little example of how you can kind of come to derive the same, derive a neural network. We are building a complicated function to describe inputs to outputs and map inputs to outputs. We're going to look at a little example of how you can derive that. So say we've got some data, and this is just simple, zero floating point data. We can go ahead and create a model where we're literally just fitting the data and then outputting a function. So we can go ahead and have a look at that, see how that model's doing. In essence, we're kind of like going back to kind of early secondary school science, where we're kind of creating a line of best fit for a given set of data. And this is almost the raw essence of what we're doing. We're capturing these points of data in terms of a function, and then the classification and prediction comes from applying that function to data that is unseen, so that we can like define it in terms of a particular class, or we can predict a given y value from an individual x value. We can also, we have the ability to kind of look at the least squared plot. This is defined later on in the notebook, but just nice way to kind of describe that data. So if we want to go ahead and kind of so we've obtained a model from just creating a line of best fit in this sense, but we can actually just use a neural network to do this as well. So the way we're going to do that, so we are first going to need to transform the data. So we're going to need to run map apply. So initially our data was just a rank 2 list, but then if we go and map apply, so we're changing the initial head from list to rule in this sense, so we are mapping inputs to outputs. That's kind of like the basis of this piece of code. This is the format which you need to apply to neural networks and a lot of the ML machinery. So what we're going to do is we're going to set up a really simple linear layer, which is going to output a vector of size 1. What we're then going to do is we're going to here we've defined the neural network itself, but it's at the moment it's uninitialized. It's like got a random set of weights and biases involved in it. To actually train that neural network, we are going to have to call a secondary function called nettrain, which, if my computer allows me to, So yeah, we're going to call nettrain to train that previously uninitialized neural network with our input-output data. So again, you get this nice little infographic of what's going on. So we're using the Adam method at the minute. We are steadily decreasing the loss function, so it's getting closer and closer to ground truths for given inputs. I should mention that actually, whilst this is running, this is so one cool thing that you can do. If you have an NVIDIA graphics card, then you can actually make use of that GPU. So you can actually just set the target device to be a GPU, and if you have an NVIDIA graphics card, then that will just go ahead and train on the GPU, which is going to be much faster than on the CPU. GPUs are going to be much better for running the kind of eventually all boils down to applying the chain rule. So it's essentially linear algebra. It's essentially gradient descent, and it basically what training a neural network boils down to is a lot of matrix multiplication, which is very well done on these massively parallel kind of systems like GPUs rather than CPUs, where we're kind of doing that all on kind of like sequentially. So right, we've now got a trained neural network, which is literally just one linear layer. This linear layer is going to be calculating some kind of weighted sum, and then once it's all done, then we can go ahead and apply that trained neural network to see how it does. And again, it kind of like is able to capture the raw essence of the input data and kind of get this line of best fit. So what we can also do is to kind of show you that it's come to the same conclusion as just the simple fit function. So it's gone ahead and described it's created a function in this sense, and we can actually we've managed to derive the same function, very, very similar. We've described the same function on the same data. So it's, we've come to the same conclusion from using a trained neural network. Okay, cool. Does the target device run on Apple M chips? I'm afraid not at the moment. We've only got GPU support for NVIDIA graphics cards. That might be coming in the future, I'm afraid. Does Mathematica utilize Intel's NPUs, and are they any different? I'll be honest, I've not heard of NPUs. What are these? Neural processing units. Okay, that's cool. Okay, at the moment, I'm not sure if Mathematica uses Intel units at the moment. I haven't been made aware of this. It's probably something that's like in the pipeline, so definitely check us out. But yes. Okay, so we just looked at a very simple one layer example deriving a model from two ways using just general fit, then going from the neural network, they come to the same conclusion. In essence, they are just the same thing. So layers are themselves just trainable models. So the ability to like perform very complicated tasks comes from chaining these together into these complex neural network structures. So that's not meant to be there. So we've got this. So we previously described this trained network in here, and what NetChain is doing is kind of so it doesn't like that, but it's in essence just nesting that function. So we can apply the train net to 1, then we can nest it again, and we can nest it again. So we kind of like what we're doing here is we're kind of feeding, creating a feed-forward network, feeding the inputs of or the outputs of one node to other nodes, and then creating this kind of like propagated system of data so that it can flow from inputs to outputs. Okay, so that was like a pretty simple linear example. So let's look at something a little bit more complicated. So if we've got some non-linear data, so we've got a kink in the data, to be able to go ahead and learn this pattern, it's going to be it's going to be hard to do that just with a simple linear layer. So here we can describe a here what we're setting up another neural network here with a linear layer outputting vector size 2. Then we're going to apply an element-wise layer of ramp, which is kind of like, I think it's like the ReLU activation function. So basically mapping everything in terms of zeros and ones, I'm fairly sure. And then again, finishing off with a linear layer outputting vector size 1. So if we set up this network, again, it's uninitialized. We're going to have to train it. Again, running through the same process. So again, we're using the Adam method, minimizing our loss function, so it's getting better and better. It's able to, get that input mapped to a correct output correctly, and then we can eventually apply that to unseen data and do some useful task. Which is taking a fair minute. I probably should have set this up to be trained on the GPU, but never mind. Okay, and now, same thing. We are able to kind of, in essence, build a line of this best fit, build a function which is able to accurately describe this data. And we've done this. We would have struggled to do this with our trained net. In fact, I wonder what it would look like. Trained net. Let's have a look, see how it does with that. Yeah, so like our initial trained network with just a simple linear layer just wasn't able to capture the information enough at all. You really do need to, with non-linear data, you need to go ahead and call upon these non-linear nodes, these layers, and then it's often best to go linear, non-linear, linear in that order. Okay, let's look at another example. So this is here we're looking at how you can kind of attempt to kind of get a neural network to learn arithmetic operating on sequences of strings. So obviously this isn't like actually a very good idea. It's more to show that it's kind of like to show that neural networks are never 100% understanding the task in the same way that a human is. It's really just based on probability. And so if we're giving it input strings, and then so this is just setting up this just sets up the data. So here this data looks like this. So we've got this string where it's 31 plus 20 equals 51. So we've got input data which is mapped to a ground truth. Then we can attempt to try and teach the LLM how to compute arithmetic based on strings. And then here we're setting up a chain of neural networks of layers which to assemble our neural network. We're using a unit vector layer, long short-term memory layer, bunch of different layers involved, and then eventually converting it into a single number and outputting a real. So here I've actually pre-done the training process. Again, this will be an uninitialized neural network, and then we go ahead and train it. And we can add there's a bunch of different options for how you can train it, and we'll look at a few of those later. So when we apply that to our inputs, then the neural network hasn't done badly. It's able to capture the essence of 5 plus 2 is like relatively close to 7, but it's not able to categorically say that 5 plus 2 is 7. It doesn't work in the same computational space as running stuff in the Wolfram language. So 5 plus 2 is 7 in the Wolfram language. Thank goodness. That would be a little worrying if it wasn't. But another interesting thing. So that was what was that? 5 + 2 gave out 7.2. But if we swap the order of things, it goes ahead and changes it. Just this is kind of like showing that. Windows is a pain. Right, apologies for that. But yeah, okay, so we didn't get the same answer when we swapped around these individual numbers, which to you and I obviously makes sense, that it shouldn't change the answer. But the neural network has learned this in a very different space. It's not actually doing the computation, and this is something to be pretty considerate of. Neural networks aren't going to be a good thing for everything. They're very good at learning complex patterns that we can't otherwise recognize, but things like computation-based things, it's not the best thing for it, and this allows us to hallucinations and a bunch of different issues to be aware of. Okay, let's look at how we can create slightly more complicated neural networks. So here, earlier on, we were using NetChain, which is really just passing neuron outputs to nodes in a kind of like feed-forward way. What we can do with NetGraph is make that a little bit more complicated. So here, I've set up and pre-trained a neural network where we've got a neural network consisting of a catenate layer, a linear layer, and a logistic sigmoid layer. Again, nonlinear, linear, nonlinear, linear, nonlinear layer. Then we've also described net ports. So these are kind of like entries or exits to the actual network itself. Actually, what might be better is if I show the description. So here we've got the net port in terms of again so I should have mentioned working with the Titanic data, this data set of class, age, sex, and whether they survived or not. Here we've just done some pre-processing to delete any missing values, because in the real world your data sets are never going to be as clean as these nice example data sets. So that's something to be aware of when performing this sort of operation. So here we've got our net ports, which are kind of like give you the ability to slot in at this location, individual age, sex, class units. Then we've got our first layer here, which is our catenate layer. Then here in the net structure, so we're kind of first of all we're setting up the layers. Then the second argument we're setting up the next structure, and then describing these ports. Then we're describing the path we want it to take. So into the first layer, which is our catenate layer, then our linear layer, and then our logistic sigmoid layer, and then we've also got another net port, so an entry or exit part of the neural network, and that's outputting the survival layer itself. So you kind of have to go ahead and start applying these net encoders. So here we're encoding in terms of class. For the age, we are actually this is just because this is just converting our scalar quantities, so raw numbers, into vectors, which is what this one is doing. Again, net encoder is outputting the class in male or female. And again, this is just kind of looking at the neural network. Right, okay, so I have thankfully pre-trained this neural network from these parameters to kind of go ahead and learn, train, be able to go from input to output successfully for training data. So now we can go ahead, and I think this is a homage to the actual Titanic film. I'll be honest, I haven't seen it, but pretty sure that Rose was first class, 17, female, and survived, and Jack unfortunately did not. But yeah, that's kind of like the general structure for using NetGraph. You don't have to be limited to using linear feed-forward neural network style approaches. So just a bit more like info on these these encoders themselves. the kind of encoder you want to use, or decoder, I should add, really does kind of like depend on the data type you're using. And there's a bunch of different types in the Wolfram language. So, if you're working with audio data, obviously you're going to be wanting to use audio encoders. Text, referring to tokens, images, and there's a bunch of different ones. So, and you can actually just go ahead and call these net encoders. They're kind of serving as functions. I can, encode this particular sentence in terms of characters. I think looks like I can't quite decipher that, but there's this is a way of describing this particular sentence, string sentence, in terms of numbers, which are going to be the only thing that the neural network can actually understand. Okay. Also, so we can look at tokens. This is again another way of describing this particular sentence in token format. And here we're calling upon subwords. So we're looking at individual subwords for supermarket. So supermarket is kind of like a compound, consists of two compound words of super and market. So if you are working with words like this, data like this, then you might want to be using a net kind of like subword token encoder. Again, like that. Okay, so again, we're going to kind of touch on whether you actually need to build a neural network. So we looked at how you can kind of like use classify, predict to kind of get a nice model just for yourself. But if what another thing you can do is you can kind of use the pre-baked in neural networks themselves. So here we are pulling in neural network, then we can apply it to this individual data set, and it can go ahead and perform somewhat well. And then this is just another example on depth perception. I'll probably skip that. It's pretty it's not super interesting. Okay, so in the Wolfram language, you have a bunch of predefined neural networks you can have access to. These neural networks are somewhat modular. These are, and also kind of alterable. We can actually retrain them themselves. So what I'm going to do here is I'm going to pull in some more of the MNIST dataset. So this is just short. Yeah. I think this is just more handwritten images mapped to raw data. And what we can do is we can we can still use this data, this neural network itself, but what if we wanted to apply this neural network to some kind of like a slightly different data format? So what I'm going to do here is I'm going to create some more blurred style data. So we're kind of like taking in the raw so yeah, we're making some more data where we are taking individual images and then mapping them to ground truths, and then we are creating a bunch of those. Okay, so no, we've created a bunch of different data where the actual raw kind of input data is more blurred. So what we can do now is we can see if the baseline neural network is any good at deciphering what they are. And it doesn't look like it's performed super well. This is a 9 to me. It's telling me it's 1. The whole. So what I'm going to show here is that you can actually just retrain your base pulled in neural network with the new training data. So you can kind of like rejig the ability of our neural network to do to be more suited for a particular training set, for more a particular data set. And again, we're still like kind of capturing the hidden patterns inside the data in terms of neural network in the neural network space. Now with this new retrained neural network, we can see that it actually performs a little bit better. So again, this is showing, do you really want to build a from de novo scratch neural network? You do already have access to neural networks which are retrainable. This is kind of like a similar example. I might brush past it because it's pretty similar. Again, kind of like you can retrain a neural network. Okay, what are we doing here? I think this is more similar. It's just you can retrain neural networks. You can extract out individual parts and go from there. Okay, this is a pretty good example. So here, I've pulled in the Wolfram image identifying net v1. And this is a neural network which is pretty good at describing, classifying individual images. Here we've got a tiger, which looks pretty accurate. So a nice thing about having representing neural networks in this symbolic fashion is that you can actually go ahead and they are kind of to an extent they're kind of modular, and so you can actually just go ahead and replace part of the neural network and then kind of like force the decision output to be more specific. So here what I'm doing is I'm kind of initializing a new neural network where I've taken this existing ImageNet v1 neural network, and then I am kind of replacing some of it so that it has a linear layer at the top, and I'm giving it a new decoder in terms of rock, paper, and scissors. So I've already retrained this. So here I've got some more ground truths data. So I've got some scissors, some paper, some rock. I've got this like kind of fashion of inputs mapped to ground truths, and now I can go ahead and retrain that rock paper scissors neural network we're using this new data. So here I'm actually going through the training process. I've already done this, and you can actually see where I've gone ahead and changed the neural network. So I've added in this linear layer and then this softmax layer and this output, kind of like using that net decoder to classify this in terms of rock, paper, and scissors. So a few options that have gone around to kind of instigate or like kind of prompt this neural network to give a specific output in terms of rock, paper, and scissors. I've said for this newly added linear layer, I want a learning rate multiplier of 1. And then for anything else, I'm going to set that to none. So in essence, I'm only really changing the weights and biases of one individual layer. And so this is kind of powerful because you are able to, instead of completely making your own neural network, you're kind of taking the predefined understanding, predefined pattern matching ability of the neural network, and then you're kind of like augmenting it for a particular use case. In this case, deciphering images as being rock, paper, or scissors. So then I can go ahead and actually apply this on some unseen images. And as you can see, it's doing pretty well. So, it's seeing some rocks, some papers, and some scissors. So, this is more just to show that you can kind of, augment the ability of pre-existing neural networks for particular use cases. You using like kind of this modular approach to like switch out individual layers as and when you need. Okay. Right. Okay. So when you're actually going about using the kind of like going about the training process itself, there's a bunch of different options for kind of fine tuning this training process because training a neural network is kind of it's quite an intrinsically computationally expensive task. So if you want more accurate predictions, then you're going to be wanting to spend more time, possibly using more complicated machinery like setting your training device to GPUs. Um, and there's many different often options you can play around. Again, you kind of get this trade-off of accuracy versus computational expenditure. And these are all very documented, so it's definitely worth checking out. Okay, so now we're going to kind of like touch on some issues that you might run into, kind of define what they are and how you can avoid them. So this is like more to do with so in essence, what a neural network is doing is it's building a function to map inputs to outputs. Now, you want that function to have a bunch of freedom to be able to describe complex data. And there's kind of like you've got to strike a balance between giving it the right amount of freedom, so that it's able to like kind of generally learn the patterns of the data so that it can perform successful classification prediction style tasks. But there's also another line where you don't want the neural network or the function to learn the data too much, because you kind of get these complicated artifacts. And so these degrees of freedom are very, it is literally just how complicated the raw function is. And this is just a nice infographic to see. Initially my function is not able to like capture the essence of the raw data it's seeing, and this is going to be performed pretty poorly when doing any tasks. But if I give it more and more degrees of freedom, it's able to build a more complicated function. It's able to more accurately describe that data in this coordinate space. And so you get better and better, although this seems to be doing pretty well at like 6 degrees of freedom. But yeah, eventually it just gets worse and worse. I think. Ooh, okay, yeah. Here we're getting more and more. We're learning the data, so it's going through the data points more precisely, but you are then embedding these kind of incorrect artifacts, and so actually now you're performing, getting into the overfitting territory where it has learned the data, but not the raw truth associated with that data. Okay, so we can also look at another example of that. So here I'm going to set up, I'm building a bunch of data of the, just an exponential function. And then I'm throwing in some random variance into this data, according to this distribution, and then doing that for a particular range. So, in reality, your data is not going to be 100% perfect. That is a fundamental thing you have to accept about data science. And your job is to kind of like do the best you can and learn the data as best you can. So here, what we're going to do is we're going to have a look at that data. So that's what we're kind of working with at the minute. I think the base data is just the exponential function, which we could have a look at here. Let's just set this up. If we remove the random distribution, then it looks a little bit different. But this is like more showing what the the ground truth is, the actual function that is going on. We're throwing in this random variation because in real life it's not the data that you read with scientific instruments is never going to be that pretty. It's just a fact of life. But this is the raw
ground truth. The correct function. This is the real life readings. And so now what we can do is we can go ahead and build some neural networks to try and learn this this data. So here I'm going to set up a rather complicated, a complicated neural network with, well, not necessarily complicated, but more, a neural network with many parameters. So it's got a lot of degrees of freedom. And then I'm going to go ahead and train that. Again, using this nettrain function with our raw data, or neural network, and then our data. And then again, going down the path, minimizing our loss function, and then we can see how that is performed. And so, yeah, it's kind of like learn to overfit the data, because it's kind of more captured the raw data rather than the kind of ground truth, the true function underlying the data. So okay, so we've done that, but how can we prevent that? And there are actually a bunch of ways you can do this, and they're like really important to keep in mind of when going about using them yourself. So one such method is just L2 regularization. So this is kind of a method which is kind of like it kind of accounts for errors by modifying the loss function as it goes. And so when we do this, then we are hopefully we're able to get a more predictions that more accurately represent the what we're trying to learn, which is the true function that underpins the data. So this is going to be more useful in terms of classification and prediction style examples. Okay, other such methods are dilution. So this is here we're going to add in this dropout layer. So we're inserting into our network a dropout layer. So what we're doing here is we're kind of what's happening is it's randomly dropping out individual layers of the neural network. So whilst it sounds slightly counterintuitive, what this is doing is it's preventing the training process to become too reliant on a particular layer or a particular pathway of through the neural network. And so in doing this, it's able to kind of like take into account other such paths which may be better for the overall prediction of the neural network. And as you can see, it's done a bit better, kind of maybe not quite as well as the L2 regularization option, but still good nevertheless. So another way you might want to reduce your kind of like overfitting is through validation. So here, what we're actually doing is we're taking and creating more data, or using more data, which is actually going to be used in the training process, kind of as in an auxiliary fashion to kind of like actually validate the training process itself, and kind of steadily augment or make kind of like make sure that the training process is going as it should be. So when we do this, again, we will minimizing the loss function when we're making our neural network, and then it does again pretty decently, doing better than it was beforehand, which is pretty cool. So again, 3 methods to definitely be aware of when trying to prevent overfitting. Okay, so having built a neural network now, we also kind of want, it's nice to be able to like get insights into how my neural network is performing. So what I'm going to do here is, again, I'm going to pull in another Linnet, another neural network. I'm then going to take some testing data, and then I can use this function, net measurements, to kind of get insights into how my neural network has performed. So here I can extract out, how accurate my neural network is. It's looking, 98%. It's doing pretty well. I can also generate confusion matrices pretty well to see, where, going down this path is it's correctly identified, how many it's correctly identified, and how many it's like gone wrong. So kind of like going through this validation process, you get some insights into, whether if I'm getting like one particular, like if I'm getting, a 7 incorrect a lot of the time, this is kind of giving me the insight that, oh, okay, maybe my training process should involve more 7s, so that I can more correctly learn the 7. So that's kind of like the nice thing about confusion matrices. A nice thing about Wolfram language, this is all somewhat baked into the language. It's all very, seamlessly done all for you. Again, we can create like nice graphics from our measurements, creating these nice false positive, and negative charts. Okay, what are we doing here? So again, we're kind of like, this is more just looking at training data to do with the Titanic. I'm actually going to skip this. This is more just showing more of the same thing, really. How you can get insights from these high-level validation query parameters using net measurements. Okay, so that's kind of all we've got today. I guess like the key points that I want to make is, like Wolfram language, very powerful way for automating a lot of different stuff to do with AI, neural networks, and what's particularly powerful in this sense is symbolic representations of neural networks, because we can, when it gets to the point of oh, maybe I want to retrain a neural network, I'm able to do that very, very easily. So yes, you do have these automated AI, ML, neural network pipelines all done for you, but you are able to go ahead and build your own in very nice, kind of like unique ways to learn your data, particularly. So yeah, automation does take care of a lot of the details, but you do have the ability to do that to build your own. Also, neural networks are going to be very, very like data hungry. More data you have, usually the better you are able to predict. But yeah, okay. So yeah, in general, like you should be asking yourself when going down the neural network approach, if I really need to, because there's a lot of automated processes all for you. But if you need to, you can do that. There are resources and tech notes to be able to learn how to do that and kind of like get very fluent in that. But also, with a Wolfram language, you are able to kind of like swap out individual layers through this nice symbolic representation to kind of like streamline or focus the neural network for a given thing. Okay, well, thank you very much for listening. I hope you enjoyed that. If you have any questions, do feel free to answer them now. But if there's nothing left, then we've got another webinar next week doing Wolfram language for Python users, and do feel free to check that out with this barcode. Anyway, guys, and there's a few more resources here as well. This is some initialization stuff. But anyway, cheers, guys. I hope you had a good webinar, and I'll catch you later.